All right, welcome back, everybody. Physics, here it is, 7.1. We're talking Kepler and Newton and tying these ideas together. So, quick review. I have up on the board Kepler's third law, which is a mathematical version to tell us, hey, how does the periodicity and the orbital radius of a planet relate to each other? And it's the square of the period as the cube of the radii. We have Newton's universal gravitation here, which I think we could just call it NUG, just for fun. That seems like an appropriate thing, but there is a L in there that doesn't make the acronym work well. Anyway, this was something that we weren't quite sure. What? This was something that we weren't quite sure of because we haven't defined what it is other than it's called the universal gravitational constant. And looking at these, we also have the orbital period of any body orbiting another body, and we get the orbital period in seconds as given by this lovely equation. Now, last class, what I asked you, or what we started looking at before you guys left, was how do we tie Kepler's third law and Newton's idea together? So, going through here, Kepler's third law and Newton, this is where I believe we left off. We know that this planet orbits this star, and we called it a planet in the sun, purely because of centripetal acceleration and centripetal force. So what we have happening here is the net force acting on the planet, in purple, must just be mass times the centripetal acceleration. Those are the only forces acting. Now, the net force, or the centripetal force, if you would rather, what causes this planet to not just shoot out away from the star? It's gravity. So, what we see here is instead of the net force on the left, we just say, oh, Newton says here's how you calculate out the force of gravity between any two objects. And we just substituted right in. On the right, I have kept the mass of the planet, mp, and I forgot my subscript on that first line. But the second line, I have the mass of the planet. And then remind me, where does this centripetal acceleration as 4 pi squared r over t come from? How did we obtain that? Could you conceivably solve orbital period in purple above for a sub c? Now, it looks a little different because I've taken out the 4 pi squared and taken the square root and called it 2 pi. But this in purple is exactly what gets replaced down here in red. So we have these, and then the algebra kicks in. I was not your algebra teacher for any of your stuff, so it's possible, and I would say likely, that our algebra might look a little bit different. But that's okay, as long as we get to the same thing. The one little issue, do you guys remember what my mistake was the other day? Before you left, I made you fix something. I had a square right there as well that was wrong. And I can see it's wrong because when I square this, it's just r, not r squared. Hopefully you guys caught that before you left, but here we are. So I asked you to do the algebra. If you were able to, awesome. If you weren't able to, I don't believe you, but trust your algebra skills. So check it out. Right off the bat, from this step to this step, can you look at it and tell me what I've done? Talk with your neighbors. I'll give you about 20 seconds. I'm going to call on somebody random. What did I do between lines 1 and 2 of that calculation? 20 seconds. Morning, Huggins, by the way. Oh, another day, another dollar. All right, lovely flow of ideas between great minds. Cool, 20 seconds. Anybody want it, or do you want me to randomly pick? I like what you did. Okay, so literally I just each side to the -1 because I recognize that I asked you to solve for t. It's easier if it's in the numerator. So if I raise both sides of an equation to the negative first power, it just flips the fractions, right? Alternatively, you could think about it as this convoluted cross multiply then divide by each thing on the other side. That's ugly. That's the same result, but this is easier. Okay, how about, and I'm just going to say this to the -1 is all I did to both sides. And I'm going to better write that stuff to the -1. Cool. I do. Got a dartboard. You ready? Yeah. I would never do that. Probably. I don't know. All right. What about the second one? From here to her. I undid the division by 4 mass of planet pi squared r, right? Just multiply by both sides. And then we get down to this lovely expression. Now, if you didn't do the algebra, I know you could. And my hope is that even if you didn't do this because you forgot or whatever, is there any part of the algebra that you did not understand as just going through it? Cool. So this right here is the big connection between Newton and Kepler. So this singular expression is what gives me the orbital period of any orbiting body around anything else. Now, in this case, we had a star specifically with a planet, but it doesn't matter. We could be orbiting a black hole, irrelevant. Doesn't matter what we're dealing with. What we do get is a few different things. We get the period t in this situation, the orbital period, in seconds, specifically Earth seconds, and it represents the time around our star. Now, going through here, we get to use this, and we're in a weird situation. We're going to weigh the sun. Just kidding. That's insane. We're going to weigh the Earth today. And when we do this, we commented last week that we're going to run an experiment here over the weekend, but it's going to take the full weekend, and I'm going to have maintenance turn off the fans. But Friday in class, you guys will help me set up something that we're going to at least briefly see today to figure out if we can't get a good estimate for the gravitational constant ourselves using rudimentary techniques. So we're not in a big fancy physics lab. We'll be kind of close, I hope. We'll see. But we'll set that up this Friday. But there's no way to do anything else moving forward without saying, well, this is what this guy got, and then we'll see if our answers compare. Cool. So moving from here, there's a natural question. If you want to be able to find the orbital period, we need a few different things. Now, getting the mass of the sun or a star and a planet can be kind of challenging, but if we knew the gravitational constant, we would be able to at least relatively work this out. So that should be the next natural step. If we want to use this or anything of Newton's, we need to know what that capital G is. So here we go. We're going to go a little bit into the history of it. We're not in a history class, and we will not go into Cavendish work. Cavendish's, I don't know, that's the name of the scientist. We won't go into his work super in detail today, other than saying here's the basic idea and the experiment that we'll set up this weekend. So our next section, still in 4.1, is how does one go about measuring the gravitational constant? The gravitational constant. And we're just going to write this G. All right. Now, Newton came up with this number mathematically just in the course of his calculations. Unfortunately, technology in 1670, when Newton was doing all of this big work, was not good enough to really be able to calculate this out. We couldn't check it. In fact, it took about 100 years after this idea of G had been presented before anybody could verify it in a lab and see that, oh yeah, Newton, you were right, good job. He was dead, so he didn't really get that pat on the back. I'm sure he knew he was right, though. Okay, when we're looking at this, we are going to jump forward, and this is going to be an oddly brief section, but we're going to talk about what is known as a Cavendish, and his name, I can tell you his first name here in a moment, Henry Cavendish. He built an apparatus or a device to help measure this. Now, question for you guys, because I've never really understood this. We're going to pause because this is a grammatical question. So, grammatical issues possibly waylaid for now. We're going to be looking at Cavendish's apparatus. So, apparatus is just a fancy word for device, right? So, it's basically how he was able to experiment with this. So, we are looking at 1798. And at this time, 1798, big ideas were being made and big advancements in mathematics that allowed us to deal with these sorts of things. But he was an experimental physicist. I assume he was also theoretical, otherwise he wouldn't be working with it. But we're going to give the basic idea. Now, I'm going to draw a picture here. Let's say that we had a rod that was propped up. So I'm just going to prop it up here. And I lied. We're just not even going to worry about it being propped up. We'll talk. Let's say that I have something that I'm hanging from, and from that is a thin wire. Okay. Now, on this wire, if I twist it up, there's a way that I can measure, like if this is a metal wire, I can determine how much force it would take to untwist it. So I could use a scale, and I could say, well, how much force do I have to apply to get this thing to move reasonably? Okay. So we have a twisted wire. And I'm not going to write it all, but we would be able to work out the force needed to untwist it. And then suspended from this, two things. First thing is down here we had a lovely mirror. And I'm not going to be able to draw one more little piece of this, but we'll talk about it. So there's a mirror hanging from this wire that's been twisted up, and we know how much force it takes to untwist it. And then below this mirror, there is another long bar, like so. Now I'm going at an angle to show that it's like trying to be like, instead of just looking at it like this from your point of view, it's kind of like this. Okay. Now, in the universe, any two objects, any two, should be attracted to each other via gravity. But gravity is so stinking weak that sometimes that's hard to verify, right? Like, if I put my pencil right here, I know that, just kidding, now we'll do it. There's a gravitational attraction between this calculator and this stylus. There is, I guarantee it. However, do you think that even with enough time, we're ever going to see these do this? As they're sitting here, like in our classroom, would it ever happen? I don't think so. Why? Why don't we see that gravitational attraction in front of us, just in general? Like, I've never seen my dresser gravitate to my bed in my room. Like, that'd be weird. But maybe it should, right? Or it shouldn't. I don't know. Why doesn't it? It's not strong enough because there's another gravitational field that's maybe doing a little bit more strength than that around it. Constantly pulling on anything everywhere here is the Earth, right? So unless we could power that, we wouldn't be able to see it. Now, in this situation, we put two spherical masses on each end. So these typically are just whatever dense metal you can come up with. We're going to be using lead for this, and specifically some lead fishing weights that are like 2 pounds each. So we have a weight. Now, if we have a weight in front of us, we could find the mass. So let's just go ahead and specify that not only do we have a weight, but we have a known mass. I don't know, maybe we would call it like M1 if we were going to do calculations or something. Cool. Now, this thing is being suspended from something. I don't know what it's tied to here. But we have two small masses on the end that are super duper dense. Beyond this, on the floor, we also have two significantly larger masses. And then this is where it gets kind of weird because this one's drawn behind it. So these ones, significantly heavier, and we will be using bigger, denser fishing weights. So we'll have lead balls in here is what we'll be playing this experiment with. Now, if the gravitational attraction were in fact true, and it is, what do you think you would see happen between this suspended mass here and this one? What should they do to each other? Any two masses always do what? They attract. Now, if this just hypothetically were a 10-pound ball and this were a 1-pound ball, I don't think the 10-pound ball is going to be the one that moves. I think it's going to have to be the smaller one. Would you agree with that? So what we see wind up happening is the whole apparatus will rotate. Now, whether it rotates all the way to touch it or not, it depends on the specific situation, how heavy your stuff is. If we had big chunks of gold, this would be even better to do this experiment because gold is way more dense than lead. But I can't afford that. Okay, now, the angle that these things wind up moving, and it realistically, we won't even see it move the whole way across, but it's going to be very, 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 very small. And that's a hard thing to measure if it's like almost nothing. So what Cavendish did was he said, hey, this mirror that I put on here, I don't know why. He put a mirror on here, and then out on the side, he had, I'm just going to use, we're going to say a protractor, but it wasn't truly just a protractor. He had a measurement device here that had all of his angles marked out, right? So kind of like a protractor. And all he did was he fixed a light source to hit the mirror and then tracked it, and he let it set. And as it set, what do you think he saw happen with where the light bounced off that mirror and struck on his measurements? If the thing truly is rotating due to gravity, what should happen with that light? It should move, right? And now if we move it out far enough, we can measure the 100th of a degree or whatever it is that we wind up seeing. Now, this experiment did everything that we needed. We knew the mass of each ball, and I'm just going to label some stuff. Let's say that this was mass 1, this was mass 2. He knew the force here that was connected between them. And there's only one more thing. I guess he knew the radius between these balls as well. He knew how far apart they were. What's the only thing you possibly need according to Newton? If we look back at Newton's stuff, and I'm just going to write the formula here. You guys can write it again if you want it. Remember, it's this constant, G, then m1, m2 over r squared. And we're just going to look here real quick. If and when we set up this experiment, will we know the mass of both balls? So those are knocked out. We got it. We have those taken care of. Will we be able to measure, the distance between mass 1 and mass 2? Knocked out. Will we be able to determine the force required to move this wire? We can. Whether we have that ability or not, we'll have to play around with. What's the only thing we don't know? We don't know G. Well, G, could we solve for it if we knew all this other stuff? And Cavendish did exactly this. Now, Newton's mathematics had led to a value that we'd already seen. Cavendish, 100 years later, says, boom, Newton, you demand, you had this. Here it is. It's ugly. Turns out that Cavendish discovered the following. I'm going to star this. G, our gravitational constant, is exactly equal to, it's a super tiny small number, but it winds up being 6.67 times 10 to the power of negative 11. And then here's just one little piece that we get kind of used to just ignoring. How many of you guys, when we do problems, don't necessarily play the unit game? You just trust that the calculations are going to spit out the right thing at you. I do it constantly, and I've seen pretty much everybody in here do it because you calculate out newtons, but you label it meters per second. That's a common mistake. Now, I don't want to play the unit game all the time. However, what I do want us to do is reason out what these units will be. So let's just look at this piece here, and on a piece of scratch paper or in your notes, I want us to do the following. I want to know, what is this unit? That's my goal. And really, I'm going to say that's your goal, is to find it for me. So from this formula, and I already crossed it all out, but here's Newton's formula for the gravitational strength. Do we know the units that are used in everything else, do you think? So all I'm going to do is I'm going to keep G as a capital G, and everything else I'm going to replace with the units, and I'm going to ask you guys to determine what are the units on this constant. When we measure a force, what are the units? Newtons. I'm very curious if Newton himself presented all of his work and said, hey guys, just so you know, we're going to measure force in newtons because I'm awesome. And I just, very curious how that conversation would go with others. It's odd. Okay, what about masses? What do we use to measure mass typically? Kilograms. So we have G times mass 1 is in kilograms, mass 2 is in kilograms, over, we have this radius that winds up getting squared in the end. How do you measure the distance between two objects in SI units? If I said, hey, Huggins and I are 0.00000000001 light minutes away from each other, that's dumb. There's a better way. Meters. And what happened with the radius down here? Squared. I'm going to give you like 1 minute. Find me the units for the gravitational constant, G. Cool. You are solving this for G, just to see what the units would be left as. I'll give you a moment. Flex your algebra muscles. Multiply by meters squared. So right off the bat, we get two ways to think about this. Newtons times meters squared. And then all of that gets divided by what? Kilograms squared. Now, units can be ugly. And in fact, this unit is super ugly. Newton meters squared per kilogram squared doesn't really mean a ton when we're dealing with it. However, when we start using this for calculations, if we play the unit game and we're careful about it, we're always going to be convinced that our calculations are correct because we know what the other units we're expecting to work out. Now, with this idea, we now have ways to calculate things that were insane and unfathomable before. So it took the advent of modern technology, and we couldn't do this without modern technology, but we're going to go ahead and just use the significance of this, and we'll do a quick example and see why would anybody ever care about the value of this constant g. And it turns out pretty easy. So let's weigh the Earth. Now, there are inevitably some parts of this that I don't love, and to be completely honest with you, I don't know off the top of my head where they got different masses to use in this calculation in the first place. But if you're interested, we can all try to figure out that question. Now, as we're looking at it, let's just check some stuff out. Right off the bat, we're going to do this without numbers first. If we wanted to write the mass of Earth using like convenient physics notation, how would you write that? Like looking for a label on it. Any suggestions for what we might use? So kilograms would be reasonable. You're absolutely right. And I'm even going to go slower. Could I just say it's this? It's just the mass of Earth, whatever it is. Because if I don't know it yet, we're going to have to find it. But you're absolutely right. It should be in kilograms as we're looking at it. What else would I need? If I'm looking at Newton's work here, I would need the mass of the Earth. Anything else? What do you think the other body we could possibly use would be? Because we need two. Could be the moon. But if you didn't know the mass of the moon yet, that'd be an issue, right? And this is that kind of odd part of it. Any two objects are always attracted, right? If I don't know the mass of Earth, but I did happen to have a 10 kilogram block right here, I would know one of those masses, yeah? So let's just say let ME be the mass of Earth, and hypothetically M be a known mass. Now, if you guys would like, we could call this M sub K just to avoid confusion for mass of something known. Let's do that. If you want to, you can. I'm going to let that be a known mass. Now, this is not really our focus, but people knew how big the world was a long time ago. You look at how shadows form at different parts of the Earth, and you can figure out how curved it is. And based on how curved it is, you can work out how large that sphere must be. So we have two masses at this point, and thanks to the ancient Greek mathematicians, we're going to just go ahead and say that RE is a radius of Earth. And the reason that we would do that is because when we think of gravity, especially on our planet, it's toward the center. So you do not have to draw this, but here's the basic thought, way scaled up. Here's the Earth, and here's where gravity pulls everything to, right towards the center. Now, Greeks had figured out that this was the radius of the Earth, and then not to scale, here's a known mass sitting on the Earth. So whatever the radius of the Earth happened to be, it must be the distance that these two things are that have between them. That's the distance of the r squared for the gravitational force. Does that feel okay? All right. Now, we have radius of Earth. Sorry. We have all these ideas worked out here. And here's what I want us to think about. If I wanted to find the force of gravity, how do you find the force of gravity without Newton's fancy schmancy ideas here? Just in general, Newton said, hey, here's the force that something has. He has three laws. I think it's the second one. Mass times acceleration. And at this point in time, remember, we're 1798 or later. Totally lost my train of thought. We knew gravity's acceleration was 9.8. We already knew that. So I think that this is true. Do you guys agree? So check it out. Here's our second law. That's Newton's second law specifically. But then Newton hooked it up even further. He says, well, hold on here. In my fancy work, I've discovered that the force of gravity is actually G times M, I'm going to say E in this case, times the known mass K over the radius of Earth squared. And that's also true. We had two ways to calculate out the same force. How many equations do you see on the board? There's two. And if we just check real quick, if I knew the mass of these, I would know this number. And that number could just be substituted in here. Can I solve this system with substitution? So we have a singular, and I'll write universal. Actually, we're going to, if anybody's superopposed, I'm fine with that. Newton's universal gravitation. Seems like a nice, convenient shorthand. I want you guys to solve this system. Solve system. And what are we trying to weigh here? The Earth. I want you to solve this system for ME. And after we get it algebraically solved, we'll go ahead and go through and I'll tell you the values of these different things that we'd already had. Cool. Play the algebra game for a second. You are solving this system of equations, and I want you to find me a single expression with a bunch of variables that says the mass of Earth. Dot, dot, dot. Some algebra happens. The Earth is a blue planet, so we'll use that blue. And I'll give you guys a moment. Once we get this worked out, the mass of Earth is just this simple thing, I'll hook you up with some knowledge. Hypothetically, let's say that we had a few things known. Do I even care what the mass of the object that we had was? Like our known mass, does it matter at all? So here's all that we need. I'm going to say right here, what does G equal to on our planet, lowercase g? 9.8 meters per second squared. Okay, so there's my acceleration. This is one that you did not know, but it had been determined. The radius of the Earth is approximately 6.38 times 10 to the 6th meters. And this lovely G value, remember, is that wonderfully nice 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. Okay, with these three values, we can get the mass of the Earth. Right off the bat. I want you guys to get the calculator practice. Verify to me that we can all get the same mass of our planet. I wouldn't normally do this if I were doing the calculation, but maybe it's helpful. Let's just think of what we need. We need GRE squared over G, right? Okay, so let's check. If I'm typing this into a calculator, here's my 9.8, right? That's G. Times, and I'll show, this is exactly how I type it in. I hit 9.8 times, what's the radius of Earth? 6.38 times 10 to the 6th. And what has to happen with that radius? Squared. And then I divide by, if you're doing this on your calculator, if I just type in this exactly, what is it going to do? If we PEMDAS through, I take that top part divided by 6.67, I get the answer, and then I multiply it times 10 to the negative 11. But that's not what's supposed to happen. Parentheses, right here. When we do this, and totally can confirm, hopefully one more person, but don't just trust my number, verify you get the same thing. I get 5.98 times 10 to the power of 24 kilograms. When you guys were getting your 5980, whatever it was, You were only missing just that negative 11 somewhere along the way. Some little weird thing with the exponents. Now, anybody know what that number actually is? Well, like, I don't even know that I know this far, but let's try. 10 to the power of 3 gets you to what? Thousands. So 10 to the 1,000 thousands gets you to 10 to the 6, which that's, what do you call 1,000 thousands? So that's 100 thousands. What about 1,000 of them? A million. What do you call 1,000 millions? We're now at 9. A billion. How about 1,000 billions? We're at 12. That's a trillion. 1,000 trillions? A quadrillion. Anybody know the next one? Quintillion. So let's see. We're at quadrillion with 15. Quintillion with 18. Sextillion with 21. Heptillion? That's 1,000 sextillions. So that is obviously meaningful to all of us, right? Numbers get so big that they lose meaning. Like, it happens just in the scale of our universe. That's a huge number. Now, what's up? I don't know. My calculator did it. I mean, we could do it by hand if you really want to. Cool. Is that heavier or lighter, or do we not have even a context or an understanding of what numbers this big represent? It means nothing to me, to be honest, other than it's a ton more kilograms than anything that I've ever experienced or thought of. But we can weigh it just by knowing this value G, which is pretty awesome. We could figure out on any body, anywhere in the entire universe, what its mass is without ever actually having to weigh it, because this universal gravitational constant that Newton discovered. It's awesome that we can weigh a star 1,000,000 light years away and still know its mass, which is crazy that we can do that. Okay. Only one real area where we can't deal with the mass of stuff. Anybody know where the idea of mass breaks down in our universe? If you take infinitely much stuff and shove it into a small area, you get such high masses that gravity and the fundamental rules of physics begin to break down. We call those what? They get so strong in gravity that even light can't escape. They're black holes. Yep, black holes, neutron stars are kind of close, maybe. But black holes are the only place where you can't do this. All right, so for Meow, you guys get the privilege of homework 7.1.2, which you will find waiting lovingly on page 185. For those of you at home, I will put the problems up on the board here in a minute. And for even anybody here, I'm fine with that. You get the privilege of doing problems 8 through 13. Cool. Homework 1.2, page 185, 8 through 13. I will get those pictures up on the board here in just a moment. Let me move that. And then I found a series on YouTube called 5 Levels, where they take an expert in a particular field and they ask them to describe a concept and have a short conversation at a variety of levels, ranging from kindergarten all the way up through PhD stuff. The last one that I found one last week randomly, that was gravity. Would you guys like to see how the concept of gravity is interpreted from kindergarten to high school to undergraduate to postgraduate, like a master's student to a PhD? At the PhD level, it gets to the point where we're not going to be able to follow it, just so you're aware. But up through undergraduate, I think we'll be okay. We'll do that tomorrow. We'll watch a short video on that. I want you guys to work on these problems for the next 5 minutes. K-Dog, if you want to continue working on your thing, you can. If you would rather work on the assignment here, that's also fine. Yeah. Cool.